Welcome to ECEN 215, Principles of Electrical Engineering. Today's topic is diode circuits and applications. So here we're going to look at actually now using diodes in a few example circuits. So we have a diode in a circuit. So we have, VD. And of course, we have this diode is actually reverse bias, assuming VSS here is positive. So current will flow through this circuit and make a complete path returning back to VSS. We have this resistor R, and if we did kind of an analysis on this, we would note that we would end up with VSS is equal to IDR plus VD. So everything you've learned with mesh current and nodal voltage still applies. It's just now that we have a relationship of VD and ID. So here we have the voltage drop again of the diode, which again, if this was like a 1N40, 148, we kind of learned earlier, this is about 1.62 volts. We have this resistor R, and of course, Ohm's law tells us that its voltage drop VR is equal to R times, in this case, ID. And that is the current going through the diode, because it's the only current that's going through this particular mesh circuit right now. So with that, we just end up with our mesh current equation, which if we wrote this out completely, for mesh current for the ID loop, just to be complete about this, we have, we have R times ID plus the voltage drop across the diode VD minus VSS would equal to 0. So that's how we got this equation right here. So now let's talk about a thing known as load lines. So a diode is in a circuit, and we can use load lines to determine what is known as the operating point of a circuit. So what that means is, so let's take a look. We have the circuit, real simple circuit we just had, and we have the forward bias region. So again, we have, of course, extending this, eventually this has the reverse bias region. So reverse bias region, which we're not actually interested in. We're only talking about the forward bias region. Because if you pay attention to this circuit, there's not a case where VSS is positive here that this diode is going to be reverse bias. So what we're looking at is you're using a line, and we're going to look at for the intersection. Excuse my poor drawing here. So we're going to look at the intersection of the diode characteristic line where we intersect what is known as the load line. So we have VSS with full power, VSS, but there is no current. And then we have over here where VD is 0 and ID is equal to VSS over R. So this is simply a case where this voltage drop is now equal to 0 volts, and we have a current that is just equal to VSS over R, because that's the only thing that is left, is this voltage drop. So given that, what you do is you look for this intersection point, which tells us what is the voltage VD at a corresponding ID. So here we're going to look at a simple circuit. This is actually two examples, examples 9.1 and 9.2. So the first one we're going to look at is where VSS is equal to 2 volts. So this is equal to 2 volts here. We have 1,000 ohms here. And then we're going to take a look at the characteristics. So we know for the load line for this 9.1, we have this equal to 2 volts. And we have here 2 volts divided by 1,000. So again, this unit here is in milliamps, so that ends up being 2 milliamps. And of course, we got that by doing VSS over R, i.e. where VDD is equal to 0 volts. So this ends up being 2 volts divided by 1,000 ohms, which is equal to 2 milliamps. So this is where this point here is determined, and we've determined this point. And we just simply draw a straight line between the two. And that's how we get this. And what we do is then we take our load characteristic for our diode, or the diode characteristic that we have here, and we look for that intersection. And that intersection for this particular example is right here, which tells us what? It tells us that VD is going to be equal to 1.3 volts. Excuse me, I have this backwards. It's going to be VD is going to be equal to 0.7 volts at an ID equal to 1.3 milliamps. So that's kind of our load point right there. Now looking at an example 9.2 here, we're going to change. Now we're going to use 10 volts here, and this is going to be 10 kiloohms, which again, our 2 points here is we've got this actually coming all the way out here, and it's going to eventually, this will intersect this line out here. VD is equal to 10 volts out here. But at 2 volts, we just did an approximation, using, well, there's no approximation, by using y is equal to mx plus b. We're able to determine this point here at 2 volts. So that's how you determine this. Again, the relationship here is that out here it's at 10 volts, this line will eventually intersect at 0 milliamps. And then of course here we have VSS over R, which again is 10 volts over 10K, which is 10 milliamps. Excuse me, 1 milliamp. Making a little mistake there. So we have our point here. And then here again, we look for the intersection, which this one here also intersects with a VD approximately equal to 0.7 volts at an ID of a little less than about, it looks like about, I'd probably say actually approximately 0.9 milliamps where it intersects. And again, you get this by just simply doing the approximation of a line. So you know this point, so you're able to write an equation for the line, y is equal to mx plus b, and then you put in a new value for x, where x is equal to 2 volts and not 10 volts. So now what about a Zener diode in a circuit? So again, let's just remember that Zener diodes have a little curve that looks like this, the diode characteristic curve, similar to the forward bias region has this. And so it's exactly the same characteristics that we've seen on any diode. The only difference is this point here is well known, and is actually the diode is meant to use this. So again, this is VD, and this is ID. So just to kind of keep in direction here, let's write a mesh current equation, but using, instead of the typical clockwise direction, we're going to use counterclockwise so that we follow the diode characteristic here, and we're going to follow the ID going through this direction, so hence why we're doing this. So we have VD, and then we have the diode drop here, which is ID times R plus VSS must be equal to 0. So all of this written out looks like this. So if that's the case, we can start using this information to make some determinations of various things. So let's continue on with using Zener diodes in circuits. So here we have an example where we have a source voltage, Vs, that's going to vary from 12 to 17 volts. So Vs is going to be from plus 12 all the way to plus 17 volts. And we have load current IL that's going to be going through this, and it's going to vary from 50 to 100 milliamps. So something out here is going to just change, and it's going to go from 50 to 100 milliamps. Now, if that's the case, we're going to assume the Zener diode is ideal, and we're asked to determine the largest value of Rs such that we get max power, determine the largest value of RS, and of course the maximum power that's going to be dissipated in RS at IZ at max voltage and load. So we're asked to determine RS, max power of and dissipated in RS, the IZ, and of course at max voltage and load. So let's look at that. So first let's write an equation. So we have Vs minus Vd over Rs is equal to IL plus ID. So we're doing a Kirchhoff's current law equation here. So we have the current that is going through this particular resistor here, which is Vs minus this here being Vd at this terminal. So this current here, this is the current through Rs, is equal to IL plus IZ, which makes sense because there's no current stored in the node. So therefore we must be in IL or IZ. So we have this from our Kirchhoff's current law. Now, if IZ is equal to 0, then Vs minus Vd divided by Rs is equal to IL. So, that means that why IZ equal to 0? Well, that means that all of the current is going to the load. That would truly be the case for maximum load current, which also would be the point of maximum load power, because remember, power of the load is equal to I squared R, or if this is an impedance, of course, we'd be dealing with Z. But we're particularly looking at resistive loads here. So we have power and load, it's I squared R. So the current is the maximum point here. So if IL is maximized, that is going to be the point where we have the maximum load. So it's looking at that. That means IZ would be equal to 0. So we end up with this, and so we can make a little table of the different voltages, Vs, at the different currents, and look at the max resistance Rs, just based upon just solving backwards, given Vd is here, so we do know here what Vd is. Vd in our case is equal to 5.0 volts, specified right here. So we have that, and we know that Vs is going to range from 12 to 17 volts. So we have two extremes. And then we have the possible RS values from that. And we have two different ILs. We have 50 to 100 milliamps. So what I did here is I created the table. So I have 12 volts at 50 milliamps. So the lowest voltage, Vs, with the lowest load current, backing this out, ends up with Rs equal to 140 ohms. At the lowest voltage, but at the maximum current, we end up with 70 ohms. Maximum voltage, minimum current gives us 240 ohms. And then, of course, at maximum voltage, maximum current, we end up with 120 ohms. Now, why did we choose 70 ohms? Because you had to make all of these conditions work. So we had to be able to support the lowest voltage at the maximum current. So with IZ equal to 0, which means all of the power is going to the load, and there's nothing else going through the Zener diode. That means we're dropping everything across RS. That means this is our lowest point right here, lowest point of resistance for this. Because if we installed 140 ohms here, that would work for 50 milliamps, but if you went to and you try to pull 100 milliamps, then the voltage here would not be 5 volts anymore. You would end up pulling less volt. In other words, the voltage drop here would not work, and this circuit would not conduct anymore because it's no longer reverse biased. So we require 70 ohms because of this. So this allows for all the load possibilities. Now, given this, we can now solve for everything else. For power max, we can use V squared over R, which is looking at the drop. And for RS here, we have Vs minus Vd, so we have whatever our possibilities for EVS is. So we have 12 volts, drawing this incorrectly here. So we have 12 volts up to 17 volts. And so VD is fixed at 5 volts. So we have this range. And of course, R is now set to 70 ohms. So using that, we end up with our maximum. So because we were being asked, what is the max power? Well, max power occurs when you have the biggest voltage drop here, which only occurs when you end up with 17 volts, not 12 volts. So you have 17 minus 5 over 70 ohms, and you square the voltages here, and you end up with 2.057 watts. So here we were asked to solve for IZ at max voltage and load. So max voltage again was 17 volts, and the load was 100 milliamps. So let's take a look at our original equation that we had for the KCL. And so we have VS minus VD over RS is equal to IZ plus IL. Well, IL, we know, we want that to be equal to 100 milliamps. VS, we know, 17 volts. VD, we know, 5 volts. And RS, we know, is equal to 70 ohms. So now we can back this out, and all we have to do is solve for IZ, which is simply subtracting from this first question, just taking the IL off, and we end up with 17 volts minus 5 volts divided by 70 ohms minus 100 milliamps gives us 71.3 milliamps. Now, what should be interesting, another thing you need to pay attention to is that we are dissipating power here. So the power in the Zener is equal to 71.3 milliamps times 5 volts, which works out to approximately 350 milliwatts. So that should be of interest here. So this is important that when you look at the data sheet for a Zener diode, if you're using it, what is known, this circuit is known as a voltage regulator, a very simple voltage regulator. There's actually other devices, but because of this, so we're always going to maintain 5 volts in this condition right here on this terminal, which is great because if you have a load that needs 5 volts, for instance, a Raspberry Pi, for instance, and you had a varying input source, you can always maintain 5 volts. The only problem is this Zener diode is going to dissipate energy, and this as heat. In this case, 350 milliwatts worth of heat. So another thing that diodes can be used for is rectification. So let's talk about that. So here we have a sinusoid now coming in. So you can imagine what a sinusoid source could be. Say the wall voltage, for instance, 120 volts RMS. And we actually don't want sinusoidal. We want to actually convert that over into DC. So one way to start that is the thing known as rectification. So a half-wave rectifier deals with the fact that you have a waveform. So a full waveform looks like this, obviously. Perfectly sinusoid, has a period, so on and so forth. Well, if you put a diode, it's only going to allow the positive voltage through, assuming you do not reverse bias, you don't exceed it. So assuming in the case of a standard rectifying diode, this is not exceeded, then the only way you're going to allow current through to the load is if you are forward biased, which means your resulting output is going to be pretty close to the actual input voltage, naturally minus 0.7 volts because of the diode voltage drop. This is going to be VD. So here you're going to be V out is going to be equal to VS minus VD. But of course that only occurs during the positive side of the cycle. So that is known as a half-wave rectifier. One thing you can do with this is you can actually charge a battery with this. And this is actually very common with at least old school vehicles, where you would actually charge your battery by using just simply a diode and a resistor. In fact, a lot of old equipment developed in the 1980s and 1970s, if they had nickel-cadmium batteries installed, would actually just simply use a diode and a resistor, and you would have a little, basically a little wall wart, little plug you would plug in the wall, and instead of being a DC, it would actually just be a transformer, and this would be like, for instance, 12 volts AC, coming in here, and then of course you'd have a diode and resistor, and every time for a cycle you would get a little spike of current, and it will just allow it to charge the battery little by little. This is actually very common. It's not used really today because there's a lot better ways to charge batteries. And then the batteries were used nowadays, like for instance, like in your smartphone, lithium polymers. You can't use this method to charge them. In fact, you would pretty much destroy them and catch them on fire if you did this. So, but this was a really old school technique and it worked really well. Now, another rectification technique is known as full wave rectification, where you actually get the full wave. So you basically, instead of having this part here that's just completely ignored, it gets folded up and actually used. So the way you do that is using this diode combination here, where you have current come through on the positive side, and it will flow through here, and will go through to the load, and then the load will return to the ground and then flow back this way. So if it was positive, it will do that. Now if it was negative, so if the voltage was in the negative part of the cycle here, then charge will flow through the negative. It'll come through, go through this element D here, again go through RL, come back through the ground input, but now go through C and return. So again, just kind of drawing this out, coming from positive, so a positive end of the waveform, so this part of this waveform, where this being the negative and this being the positive cycle. So you're going to come through here, you're going to go through A, go through the load, come back, return through B, and cycle back. Versus on the negative side here, it will come through, it will go to D first, through the load, return back through the ground, and back to the source through C. Again, this is a really common technique. It's actually used for quite a few years for actually converting AC to DC in a lot of household applications. In fact, if you have still to this day, if you have anything that your parents might own, like old hi-fis or old computers from the 1980s and 1970s, probably even a little bit even into the 1990s, using full wave rectifiers was really common. And what you would do, so obviously the output here is this humped version. So it's not exactly DC, right? It's got these humps. So how would you get rid of these humps? What you would do is you would put really big capacitors out here. A bank of them, actually. Something in the neighborhood of probably about 2,000 microfarads, or maybe even a little bit more. And what would end up happening when you did that, you would end up with a fully DC signal. Worst case, you would end up with a little bit of cycle ripple that looked like this, where this was like maybe 13 volts versus 12 volts, worst case. But the thing is, if you then went into one of those rectifying Zener diodes, where this was VS, and then we had, a Zener diode here that was set to 5 volts. The signal that came out here is a perfectly smooth and beautifully cleaned 5 volts DC over 0 ground without any issue. So you could have this ripply, nasty signal coming in, but because of this resistor R and this Zener diode, you'll get a nice, clean looking signal. You can actually use this right now to actually power various equipment. It's very inefficient and it's not used normally today. There's a lot of DC to DC converters and AC to DC converter circuits that are switching regulated to have basically transistors driving things. But this technique is still valid and is still being used today. So the last real topic is LEDs. lot emitting diodes. In fact, all diodes actually emit photons. You just really can't see them. They're usually in the infrared range. But these diodes here are specifically designed to emit in the visible light spectrum. Of course, you're very familiar with this today. They've been around since the 1960s, probably even the 1950s. They've been around, but they've been heavily used today. All of your televisions have LED systems in them. Your smartphone has an LED backlight. Pretty much everything's nowadays uses LEDs in some form or fashion. LED lasers, where this is actually a tuned LED chip to actually emit a very specific waveform, and it's narrow and it's got a cavity and actually is a laser. So these are actual diodes in the end, and they operate exactly like you would expect a diode to operate. They have a VD. They, are forward bias. If you forward bias them, and the brightness of the light is usually proportional to ID. So as you increase the current going through the diode, it gets brighter. So you can actually change the intensity of your backlight. For instance, all that's happening is your microprocessor in your smartphone is actually changing the amount of current, the average current that's going through the LED. So here's an LED data sheet showing that very similar conditions that we were looking at earlier. For instance, the chief difference is the forward voltage is usually much higher. So typically it's like 2.2 volts depending on certain colors. For instance, blue is 3.2 volts. Green is anywhere between 2 and 3.2 volts. The current luminous intensity is if you have current at 20 milliamps, you would end up with this luminous intensity and measured in microcandles or millicandles. So, and of course, this is the dominant wavelength, blue being 470 nanometers, red being at 630 nanometers. So you can just see the wavelength spectrum and what the lens color is, the size of the chip, all that kind of information. So here's just a zoomed in view again, particularly looking at this, in this case, red, 2.2 volts. Maximum, if you're designing something, you usually use the max voltage, so you make sure that you have a sufficient voltage to guaranteed forward bias. And again, this is actually VD. So this is the forward bias voltage, where mostly for the signal diodes we're looking at was about 0.6, 0.7 volts. This is now 2.4 volts. And you want to have, for maximum intensity, about 20 milliamps. So here's just a simple example of a problem. This is something that you would, for instance, see on the test. Just basically making sure that you understand the concept of diodes and being able to determine the voltage. So if we wanted to have 20 milliamps, so we were just looking at that circuit a moment ago, where we have ID equal to 20 milliamps, and the forward voltage VF is 2.2 volts, which means this here, it needs to be 2.2 volts. Then we have VSS, this power here is equal to 12 volts. What is R? So this diode, again, will light up, and notice the symbol difference for an LED. The only difference that was added was these two little arrows here to indicate that photons are being given off. So that's to let the designer know or someone who's reading your schematic know that specifically this is being used for an LED application and not just a standard signal diode. So what we have here is 2.2 volt drop here. We have the resistor R here. So let's just simply work out the equation. So R is equal to VSS minus VF over ID, because we know what this voltage is. We know what this voltage is, that's VF. And we know what ID is. We specified it, 20 milliamps. So with that, we end up with 12 volts minus 2.2 volts over 20 milliamps gives us 490 ohms. So now you can actually design a circuit where you actually specify this is 490 ohms. This is a very common thing that you do when you're designing controlled lighting in different products and stuff. And you would actually go and compute, what is my control voltage? Sometimes it's 3 volts or 5 volts, and you need to determine, probably in this case, a smaller resistor that would accommodate. So in summary, we looked at various diode circuits. We looked at obviously Zener diode circuits. We looked at using load lines for computing the intersection point for VD and ID based upon the information that we have from the circuit. And then we also looked at various diode applications, everything from using the Zener diode as a regulator, using a half-wave rectifier, a full-wave rectifier. We talked about being able to regulate an AC signal straight to DC, and then using that with the Zener diode to actually fully regulate to a nice clean 5-volt signal source. And then we also talked about LEDs and being able to use it for light emitting applications. And we talked about how you can compute the inline resistor for an LED given your specific design. So again, these are just kind of an introduction to diodes and their general use. There's a homework assignment for this, and then obviously there will be some questions on the test. Please come to the Q&A for all of your questions regarding diodes, and just have a wonderful day. Bye.